Hello everyone. We have a session focusing primarily on high performance computing today, and this is broadly our agenda. So we'll just be talking about some of the complex computational environments that we have at Goldman Sachs and how we're using the latest technological developments in terms of parallel computing and high performance computing in that space.
Yeah, hi. Well, let me see if this works.
Okay, you hear me? Yeah, seems like it works. So I'm just going to spend a couple of minutes describing a few of the different environments that we have. And I think that firstly you might ask yourself, what is a bank doing here and why are we talking about technology? And just to give you a bit of a context, we're about 30,000 people at the firm, and of the 30,000, close to a third of us are technology people. So we have close to 9,000 technologists at the firm. And if you think about the business we're in the information business, right? And so obviously technology plays an incredibly important role in how we are able to serve our clients and obviously trade in the market. So I'm going to talk about a couple of different aspects of that briefly, and then Moinak is going into a bit of depth into some of the parallel computational environments that we have. We really have, if I think about it, outside of our vanilla compute environment, which of course everyone has in terms of general purpose server farms, you really have three distinct environments that are different from what you'd maybe see in a general purpose environment. To the left here, I tried to illustrate it sort of differently. To the left here we have our computational grid, it's our risk grid. And so risk in our environment is a very important factor. And so just to describe risk very briefly, risk is, or market risk, is where we every day calculate how much money our clients and the firm have at risk. And what does that risk means? Well, that means how much could we lose in a given scenario. And so if you think about that, what we're really doing is we're modeling millions of variables. So every stock price, every option, every foreign exchange rate, millions of different variables across thousands of scenarios. And we do that every night. And the reason we do that, well, first of all, we're regulated to do that. So the regulators here in India, in the US, in Europe, etc., they all expect us to be able to state on a daily basis how much money we could lose and how much money our clients can lose. So we need to calculate this for ourselves as a firm as well as for each of our clients that trade with us. And so this problem is highly parallelizable. And so what we have is we have an environment with, I won't give exactly how many cores, but I'd say it's in the 6-digit number of cores that we have. So this is a very big computational environment. It's about half of a server estate that does risk calculation. And so it's highly parallelizable. So we have our own job dispatcher that takes in the risk jobs, it dispatches it out to the farm, and then it calculates and brings back the results. And the risk jobs can take anywhere from a couple of minutes to a couple of hours. And then so the dispatcher basically dispatches it out, waits for the results, gets the results back again, and then puts them into a very large database that we have, and a parallelized database where all the risk results are stored. Our next environment that's kind of, well, not necessarily different from what the industry has, but we developed this ourselves, is our private cloud environment. The reason that we have our own private cloud is, first of all, from a regulatory perspective, again, the data that we have is highly proprietary and highly sensitive. And so we cannot easily use a cloud like Amazon's EC2, not because it's not a great technology, it is, but really because we need to contain the data ourselves and internal to our own environment. And so we built our own private cloud, and we ended up writing our own placement engine and our own modeling around it because we started pretty early before the industry had really glommed around standard software for that. So we have, again, our own private cloud. And then all the way to the right, we have our algorithmic trading environments. And those are actually, think of those as highly shared environments, shared memory. So we have hundreds of nodes together in a large shared memory, shared network environment. And you can think of those as, in this environment, unlike this one here, there's high internodal dependency. Here, each job calculates on its own. So they're really two completely different environments, but they look, from a job perspective, it's the same kind of job that runs on each one of the risk nodes, and it's the same kind of job that runs within the algorithmic trading environment. internal to those environments. And I'm going to go into a little bit of detail on each one. So if you look at the risk grid, again, as I spoke about, and these graphs are really just trying to illustrate the kind of things that we model. So if we take an example, let's say on gas prices, and let's say our clients are trading, that we have commodity clients that are hedging their gas prices. Well, one thing we need to model is, okay, so what are the different scenarios that can happen from here, from let's say a given date forward in terms of the gas prices. So let's say someone's buying a 30-year option on gas. Well, we want to model out what the different scenarios could drive that price to be. And so that's just one example. But basically, calculating those prices over time helps our clients understand how to purchase and to understand the bands of where they can expect pricing to go. And it helps the regulators understand how much money is at risk across the environment. And so really what we'll do is, this is just a couple of examples. We'll take, again, millions of variables like this and model each one of them across different scenarios. And you can imagine that if you take that environment, you're going to have a lot of computational power doing this day in and day out. And part of the reason, and I think part of what differentiated different banks through the financial crisis we had over the last couple of years and how much money they lost had a lot to do with risk modeling. And so I think the places that did more sophisticated risk modeling ended up being less exposed to the market that we saw go through a housing downturn in the US, etc., were less exposed because more scenarios are being modeled out in a more complex way. And so, again, as I said, the compute farm models this. I think the other really interesting thing is it's all distributed out in colos. None of this computational power sits internal to us. It's all external colos across the United States. And we manage this environment, again, I said, it's 6-digit amount of cores, but we manage this environment with less than 10 people because it's very much a cookie-cutter, repeatable environment. And so these thousands of servers are managed by, actually, I think today it's 6 people that manage the entire environment. So it's a highly repeatable, highly scalable environment. On our private cloud, we call our private cloud dynamic compute. We try to avoid the term cloud because cloud can mean so much to so many people. So we use the term dynamic, which is really trying to illustrate its environment that is agile. I think the key thing here that we do, and again, it's not that dissimilar to what you'd find from EC2, if you want to use an industry parallel to understand what we've done here. Our application developers will model out their application. And so modeling really means they'll state how much memory they need for the application. Is it a 2-tier, is it a 3-tier app? What kind of computational power they need. Do they need resiliency? Does it need to be fixed to data center? What kind of storage they need? What kind of networking, etc. But they'll model out what their application tier looks like. So ultimately we have a tool called Canvas where the application owner will draw out what, basically a topology of their application as well as the attributes required. Once they model it out, and then they create a deployment model that then gets basically, through a placement engine, becomes a deployment instance that then gets put into our resource pools. So, and the reason this is really powerful is if you think about in a traditional computational environment or traditional data center, you're very fixed to your server, you're fixed to the storage, and because it's not modeled out, when something fails, your SA has to go by either from a tape backup and replace it, or alternatively has to use sort of tribal knowledge to replace the environment. And because we modeled, in this case, we modeled out what it looks like, if we have any failures in our environment, so if something happens here, because we have a defined model, we can really just go re-instance this computational environment somewhere else in our farms. And this allows us a lot of flexibility and agility around dealing with topology failures. Long term, what we're looking at, and this has more to do with our ability to manage our data and look at how do we protect our data. We could long term envision that this might, again, be an external resource pool like EC2. The things that we need to watch out for is how can we get to an environment where we can protect the data and so deal with encryption within a public cloud. And so we do want to get to a place where we could use public clouds as well, but it really has more to do with how to secure our data than anything else. And then if I briefly touch on the final environment, which is kind of unique to the financial industry, which is our algorithmic trading environment. And so to talk about algorithmic trading briefly, if you think about most of the trading that happens in any electronic trading environment, and so, the US is all converted to electronic trading, so any exchange, you can have a traditional trader, like a person calling into, you see the cliche in any of the movies with a person yelling into a phone to buy and sell. I mean, that's pretty much done with in any market in the US. There are a couple of markets still that do that. So in London, for example, they trade metals, and they literally sit in the pit. They call it a pit, but there's a circle of people. They sit around a circle, and then they yell buy and sell orders to each other across that pit, and they throw pieces of paper in the middle that get collected at the end of the day to see who bought what at what price. But that hasn't changed in 500 years. It's pretty much exact same trading environment. But that's an anachronism in this time, and that's pretty much done with. And so most trading in the US, in Europe, and in Asia for that matter, is either has moved to fully electronic exchanges or is moving in that direction. And so if you think about an electronic exchange, the trading, well, in the beginning, trading in electronic exchange was executed by people that were then entering their order onto a computer, and the computer executed the order. But more and more, the buy and sell orders are really done by algorithms. And so what is an algorithmic trading environment is, we have the trader is really a person, and nowadays more than not, it's a mathematician or somebody that is, can do various forms of statistic and mathematical modeling that comes up with algorithms. That person sits together with a developer. The developer encodifies that algorithm into software, and then that software gets put into our environment. And so if you think about the way the environment looks like, we have exchanges. These are US examples of exchanges that feed us market data. Market data is basically a constant stream of this symbol or this equity trades at this number. And so every time it goes up or down, we get a new tick. We call those ticks, and it comes in up or down for each symbol. So that market data comes in. Just to give you a volume, we're talking about several gigabits per second of market data that we get into our environments from the different exchanges. We need to process that data, and so we call those feed handlers that process that data. They put that data onto a bus, and then we have our algorithms that sit onto that bus and look for trading opportunities. And then ultimately, then we have the engines then that will take this data then and decide, are we going to quote out? Are we going to actually buy or sell? Are we going to hedge? And then ultimately, if it ends up in order, then that order goes back again out to the exchanges. And so that's the way the algorithmic trading works. Now, the really interesting thing here is that from the time we get this market data in until we generate the orders out, if we are slower than our competition, then they might get the order at the better price than we are. So ultimately, it's really important to manage this space here as low latency as we can. And part of this is, part of the way we deal with this, and we call this talk the speed of light. Well, actually, literally, the speed of light matters in this case. So this computational environment, in many cases, sits co-located with Exchange, because we don't want to deal with, let's say, 10 miles worth of transfer of data, because that takes multiple, maybe a few microseconds. And so ultimately, end up putting this environment next to the Exchange and across maybe just a single switch hop, so that we can minimize the amount of time. And so the latency for this is across the entire stack. So we optimize the kernels, our Linux kernels, we optimize the network stack, we optimize the computational stack, we optimize everything across the board to make sure that this is as low latency as possible. And so that grid that I showed you in the prior picture is really, then we have multiple machines that sit here together. They share memory. We use RDMA, and we have an InfiniBand transport in the backbone. And so this parallel engine sits there and is processing the market data and then executing trades in a shared memory model. Ultimately, the low latency is really compelling, because again, if it takes us, let's say, 500 microseconds to do this, and it takes a competition 300, well, then obviously, if there's an arbitrage opportunity to buy something at a better price, then our competition is going to get there before we do. So we think of this as an arms race, and not necessarily in a good way, but everyone has to, if your competition, you don't have to be the fastest, you can't be the slowest. And so there's a constant competition about trying to reduce that latency to to get to the best possible number between us and a number of other banks and hedge funds. But this is a pretty interesting environment because you have to really optimize that. And so we have people that understand assembly language, or people that, this is all developed typically in C or C++, because here we care really about optimizing every single line of code and every single execution branch. And so really Moinak is going to get a bit more into some other math modeling computational environments we do, but I just want to leave you with a bit of flavor of the different environments that we have. And then I'll be around after some questions, and anyway, Moinak, if you want to take over from here. Yeah, you have a question now? Sure.
What is the latency that you're talking about? I mean, to get a relative idea.
So the latency, well, it depends on the exchange, and this is why what's really important here is we don't really care about latency internal to the exchange, because that's the same for all our competition. So if that takes milliseconds or even seconds is really irrelevant. What really matters is from the time the data gets fed out of the exchange until we execute the trade. And the exchanges have a principle of fairness, and they're regulated to do that. So they have to be as slow or as fast as all the competition. So that's taken out of the equation. So really the latency comes down to our own latency from receipt of market data until execution or trade. In some cases, we're talking literally under a millisecond of end-to-end. So from we get the market data in until we execute the order, could be on the order of, again, under a millisecond. And it varies a bit based upon the exchange. It varies based on how complex the computation we have to do. But in some cases, all we're doing is we're looking for a very specific price. All we're doing is pattern matching. And if it's just pattern matching, then that latency can be relatively low. And so there's some exchanges where pattern matching algorithms or simplistic algorithms make sense. And in those cases, we in our competition are just doing pattern matching, there the latency is a lot lower. In other cases, we're doing a lot more complicated calculations. That's why we're doing FFTs and so on to calculate more complex parts, and then the latency might be higher. But again, it's very similar to what a competition does. So we end up sort of in some cases lower than a millisecond. In other cases, it might be several milliseconds, but it's never seconds. The other thing, of course, is distance. So, for example, if we're trading, let's say on the Mumbai Stock Exchange, but we end up having our computation, not all exchanges colo. And so in many cases, maybe we're located in a distance away. So this might take, let's say, 20, 30 milliseconds to get the data, and then we might feed back in 20 to 30 milliseconds back again. And in those cases, because the algorithm is not as time sensitive, it's okay to deal with that latency distance. So, but yeah, in some cases, literally, we're trying to shave off 5 microseconds, 6 microseconds, right? So we care about switch hops. We care about schedulers within the kernel. We even go off and sometimes buy CPUs that run at extra high frequencies so that we can run, a single-threaded performance in a very efficient manner. Yes, sir.
In the trading aspect, do you have a provision to accommodate by request?
Do we have a provision to do by request?
Yeah, the request which comes from the customers.
Yeah, I mean, the customers, so these algorithms are typically given to our customers. So in many cases, what we do is we give our customers, we write the algorithms, but then we give the customers use of those algorithms, and then they put in the variables or attributes that they want to use. And then that gets executed upon our platform. So it's not as if we necessarily are writing all of this for ourselves, proprietary trading. These algorithms we typically expose to customers as well, and then they will themselves say, okay, I want to trade within this band of this symbol. So if it comes within this band, then have your algorithm go execute that trade on my behalf. But because of the latencies, it's typically not a human being entering the exact order. It's typically a human being will enter the parameters, but then the algorithm itself will then look at the trade flow and determine when to execute the order. Because by the time you see it on the screen and you push a button, it's way too late. That's a couple of seconds worth, and by then, if it was the appropriate price, it would have already been taken by someone else.
Because traditionally in India, we use the slips to do the trading.
Yeah, I mean, India is just like any other exchange in the world, is getting to an electronic stage. So, yeah, I mean, certainly if it's a traditional exchange with paper and slips, then what really happens is, in some cases, actually, the algorithms might generate it, but then it goes to a human being. In some cases, in a traditional exchange, a human being will ultimately execute the order. In New York, the New York Stock Exchange, we have what we call specialists on the floor, and there's some of the trading that has to be executed by a human, and so the algorithm will give the human a book of orders, and then he'll end up doing the trade locally, or just like the commodities exchange I described in London. Maybe the algorithms are giving the order, but ultimately it's that pit of people that are doing the actual trade.
You will not be able to reduce the time lag.
In those cases, the time is, it's not a low latency environment. You know, maybe the algorithm is still working, but it's certainly not a low latency takeout environment. Okay, yes?
You have a shared data setup, so how does that affect, because it's very concurrent kind of setup, so are you doing any specific stuff to manage that shared data so that you are highly concurrent as well with the amount of data, shared data you have?
Yeah, I mean, I guess we have what we call a shared book, and so these systems, you know, they're multiple, think of it as a big shared memory system that sits shares a book of data. And so really, because it's an RDMA environment, and think of it like, you know, the memory across all these systems is shared, when there's a trade that happens, something happens, they will ultimately all look to the same shared book across multiple systems. So it is absolutely written around a shared memory model to ensure that, you know, these systems at the colo are all thinking in parallel. And so that's why we use InfiniBand as a backend transport, and we use RDMA as a mechanism to ensure that all the systems share exactly the same trading book. Because otherwise, to your point, we could end up with you know, split brain type environments. So it's absolutely an RDMA based environment. Now we could take a different approach and buy a really big system with a lot of memory, and like a P series from IBM, etc. And that's another way of doing it. We chose a model of using commodity servers and just sewing them together using high bandwidth transport instead of buying a very big machine with a lot of memory in. And that's really just our bias. I mean, you could build the same thing, let's say building a 2 terabyte machine with many, many cores in it. Our approach is really to use standard 2-socket x86 machines and put InfiniBand on the back end and build a shared memory model in that way.
In
Okay.
fact, even with the commodity servers, especially with the Sandy Bridge platform, we are reaching to the point where we can have 1 terabyte RAM in a server, normal x86 server.
Yeah. Anyway, do you want to get into and anyway, I'll stick around for more questions as well, but Moinak, if you want to go from here.
Yeah. So typically when we talk about supercomputing, and I'll come to the point why I'm talking about supercomputing here, but when we think of supercomputing, right, the things that come to our mind are typically these kind of stuff, right? Big, powerful, fast, expensive. You need a huge data center to store it, and you need a lot of probably millions to run that facility, a massive lab and all those things. And you do a lot of data crunching on that, right? So these concepts are partially true, and they are not exactly, they don't exactly get to the point of what is exactly a supercomputer, right? So all of this can be true or can be false as well. We'll see. So in supercomputing, the key concept is parallelism. It's not about size, cost, or complexity. It's about doing things in parallel. And this parallelism is not just about creating threads. I can create 10 threads or 100 threads in my Java program, but that is not parallelism. This parallelism, what we're talking about, is parallelism in hardware. We have multiple different compute units, physical compute units in the hardware, and the processor or the army of processors are capable of doing multiple things independent of each other. So we also need that kind of processing problems, that kind of data processing requirements, where we have a large data set and we can split it up into smaller pieces and process each piece independent of the other. So we don't need to do synchronization, we don't need to do a communication between them. The only communication that is required is just to copy the data. So that is one thing, and that can be done through multiple processors. It can be done through a cluster, or it can be done through this thing, specialized thing called vector processors. Right? We'll see what is a vector processor shortly. And here there are some of the frameworks, common frameworks that have this kind of parallel computing model. One of the best example of parallel computing is MapReduce, which is used by all the major search engines like Yahoo and Google and all. And what they do is they split the data. They split the search data or the web data that they have crawled and accumulated, and they spread out the computation in a cluster. At the end of the processing, they have generated partial indexes. Then there's this reduce step where in stages, they merge these indexes together to form one master index. And then there are a few other things like SIMD, which I'll be talking about. And then we have OpenMP, and we have this thing called GPGPUs, which I'll also talk about here. So this is the guy who was responsible for all these things, who first thought about this aspect of doing parallelism. So when we say supercomputer, the word super means non-linear. A linear program is a single-threaded program that does things one step at a time. And this is non-linear in the sense it does multiple things at a time, and it has physical resources to do that. And this is the person who thought about it, Seymour Cray. He used to work in Control Data Corporation, and this machine that you see here, this was the first parallel computer that he created. He was initially at Xerox Palo Alto Research Center where when he conceptualized this paradigm. So let's just briefly look at what are the types of parallelism that we are talking about here. There are two different ways of categorizing parallelism. We have here data parallelism and task parallelism. Data parallelism, as I told you, we have a huge data set. We can break it up into small chunks and process each chunk individually. So that's basically a divide and conquer strategy. And we have task parallelism, where we create multiple threads, and which is commonly used in all programs that we write today, right? In all of the software, this kind of parallelism is used. There's another subset of that which is called pipelining, which is mostly used at the processor level. We have this pipelined x86 processors where different tasks or one particular task is broken up into stages, and different stages for different tasks are done together at the same time. So we'll see some analogies in that space. And then we have these other categorization where we have explicit and implicit. Explicit is when we manage the parallelism. We do thread programming, we manage the threads, we do synchronization, we use mutexes and condition variables and whatnot. And the other thing is implicit, where we tell the engine that we are using, maybe the VM or the compiler or the processor, we tell them that we want this behavior from you. This is our processing requirement, and this is what we want to do, and this is how we want it to run. But we don't manage threads, we don't explicitly do synchronization. So there are frameworks both at the hardware and the software level to do that, and we'll look at it shortly. So of these two things, the most important and most interesting pieces are these two, the data parallelism and the implicit stuff, because today in the industry, most of the work is going on in these two spaces. Threading and concurrency and clustering has been like almost beaten to death. There are so many frameworks, there's so much research done in that space. So these two are the most interesting areas today. So if we talk about vector processors, we have this concept called SIMD, single instruction, multiple data, which means that we give one instruction to a processor and it's capable of operating on multiple units of data in parallel in hardware. So this is basically the key for vector processing, and supercomputers are almost entirely built out of vector processors. So we not only have multiple machines or multiple nodes in a cluster which are doing computation, each node internally has processors capable of doing multiple things. So the processor has multiple physical arithmetic logic units. So in this example, we have this XMM1 register. I'll just explain what is XMM1 shortly. We have this 128-bit register, and it is holding 4 integers. Each integer is a 32-bit quantity. So because it is 128-bit, it's able to hold 4 of these side by side. So we have loaded 2 registers, each with 4 integers. And what we want to do is we want to add them together. So what we do is we give this PADD instruction, which means parallel add decimal instruction, and we provide these 2 registers. The end result is that at the physical level in the processor, the ALU does 4 additions at the cost of 1 instruction and produces 4 results. So if one add takes, say, 4 microseconds to work, this parallel add will also take 4 microseconds, but it will produce 4 times the throughput, which is it will work on 4 data items in parallel. So this is the key for single instruction multiple data. And this example that I showed here, this is not from any supercomputer. This example is right there sitting on my laptop on the Core i5 processor that I have on the laptop. This thing is available on Intel and AMD processors today. So the today's x86 processors have vector capabilities, have supercomputing capabilities built in already. And we have a lot of software. Mostly earlier it used to be all these games, video games, graphics stuff, which used to use these things. Now there's a lot of software which are internally using these facilities, including the Java 6 VMs. JDK 6, if you're using JDK 6 hotspot engine, will be automatically using this vector processing features to optimize your Java programs. So has anyone heard of this thing called MMX? This is, has anyone heard of this thing called MMX in Intel's processor roadmap? There used to be a lot of marketing hype around this MMX in the 1995 and 96 timeframes. These are called multimedia extensions. Essentially, what Intel did was to introduce this kind of single instruction multiple data processing with 64-bit registers in the early stage when we only had 32-bit processors, no 64-bit processors. They added these extended registers and this parallel kind of compute capability only for speeding up multimedia and graphics. After that, it has gone through several iterations over the years, and it has been expanded, and a lot of functionality has been added. So now these things are good for general purpose computing as well. And today this thing is called, it's no longer called MMX, this is called SSE, Streaming SIMD Extensions. So we have SSE in AMD and Intel processors, and in Sandy Bridge we have larger 256-bit registers. So going forward, SIMD and the combination of multi-core CPUs that we have on our machines today, combined with the SIMD, gives us a lot of power and flexibility, even with the straightforward x86 process, to do some of the supercomputing style workloads. Maybe not at a teraflop processing performance, but at least to get some of that large-scale parallelism using a cluster of x86 computers using all these features. So there are multiple ways of using it. There is this stuff built into GCC already, the current generation GCC compiler. Then you have it in Visual C++. And there is this interesting thing called Silk Plus from Intel. So OpenMP and Silk Plus, these are two interesting things where it's basically implicit parallelism. I tell the compiler that I want a parallel behavior, but I don't tell how. The compiler decides how to do it. I have a small demo here of OpenMP, which will show you the power of this implicit parallelism.
Is this useful on other functional languages?
Yes. So functional languages have this kind of parallelability built in. Things like, say, Haskell or Scheme, Scala, these kind of functional languages have parallelism built in. This one, OpenMP, is basically it brings some of that semantics into C++. So I have this small program to do matrix multiplication, which is a very standard BTech B kind of stuff that everyone learns. So we have 2 arrays, each of n by n to matrix, not arrays, and we want to multiply them together. So we have this nested loop, double nested loop here. These are straightforward, simple, out of the BTech textbook this implementation, right? It does a matrix multiplication here in this loop. Here, what we are doing is we are initializing the array first with some random numbers, and then we do the actual computation here with this 3-level nested loop. And if you see here, I have the same loop down. I am doing it 2 times. This is a straightforward single-threaded serial operation. And here I am doing the same operation, but I have put this one line here. Is this visible at the back? Okay. So I have put this line, hash pragma OMP parallel for. So this indicates that I want this nested serial loop to parallelize. Let's see what is the effect of doing this. So it's already compiled. If I run it, it asks me the dimensions of the matrix. So let's give it say around 1000. If I run this utility here, you can see that this is a 4-core laptop, and one of the cores is pegged at 100%. And now suddenly, if you see, all of the cores are used now once it goes to OpenMP, and it took a very short time. So if I'm doing it in the normal way, single-threaded, it takes me 11 seconds. But if I just put that one line, hash pragma OMP parallel, it parallelizes that for loop and uses all the cores, as you would have seen, and it just took 5 seconds, around 6 seconds to complete the whole thing. So approximately 12 and approximately 6. So it reduced the time by half. Now this is actually a dual core laptop with 2 threads per core, so 4 hyper threads. So 2 physical cores. So it reduced the time by half just by doing this simple thing. This is the power of implicit parallelism that we're talking about. And this is just a small example. OpenMP is a big topic, so I won't go into the details here. Yes? No, it's not exactly 4. It's 2 cores and 2 threads per core, 4 hyper threads. If it were a 4-core, then the timing would have reduced divided by 4. It would have taken 3 seconds. So that is the CPU part which I've covered here. Now let's go on to something more interesting called this general purpose graphics processors. This is something that happened. There's a rapid development over the last 5 years in this space. Earlier, graphics processors are only for video games, movies, and that kind of stuff, multimedia. But over a period of time, people started finding out that I could do large kind of compute workloads on a graphics processor. Because even to do video and games and all, there's a lot of mathematical computations that have to be done. If for example, say ray tracing, if you're doing some 3D kind of movie rendering, we have to do ray tracing. There's a thing. And that ray tracing requires solving a lot of these equations, straight line equations. And all of this equation solving can be done in parallel. So those graphics processors are good at doing that kind of stuff. So people started using GPUs for regular computation, for non-graphical computation work. And the graphics processor manufacturers started realizing this new emerging area, and they started producing newer processors, GPUs, which are good at regular computation rather than graphics. So if you see here, the growth in performance in terms of gigaflops is 10 raised to the power 9 floating point operations per second. So this is a number of gigaflops that GPUs can provide today. And this is actually slightly old data. In the recent times, there's been even further improvement. But compared to that, the CPU performance in that kind of space has lagged behind a lot. So in effect, this 2500 gigaflops is basically 2.5 teraflops. And teraflop scale performance is nothing but supercomputer scale performance, which we can get on our regular machines. I'll show you some demos shortly. But before that, this is the parallelism stuff that we are talking about. There is some analogies to explain it. let's take this example. We have this one poor ant which is taking food to its nest, right? So it'll do it in a loop. It'll take some item as much as it can carry. It'll come back for the next item and keep doing that. It can keep collecting for the whole day. Contrastingly, if you have a whole group of ants, whole army of ants coming to collect the food, each one can collect a small piece and take it back. So in a sense, they can take back the entire stuff in one shot to their nest. So that is a parallelism analogy that GPUs are good at. So GPUs have lots and lots of compute units, in fact hundreds. In processors, we are maybe talking about 32 cores or even 64 cores. GPUs have hundreds of cores, and they are mostly good for mathematical computing. And they can operate on multiple units of data in parallel. They have local memory. Contrasting to that, in a CPU, we do have multi-core when we have SIMD, and there's a third form of parallelism that I have mentioned earlier called pipelining. So what it does is, in a CPU, when it executes an instruction, there are multiple stages. It has to fetch that instruction from memory. It has to first decode the instruction, because these are all complex instruction set machines, so they have to decode it and figure out what the instruction is trying to do, and then they have to fetch the operands or the data that the instruction wants to work on from memory, and then it goes to the ALU to actually do the work. So there are multiple stages, and what we can do is we can do the stages concurrently. Like, I fetch instruction 1 and then decode it. While I am decoding instruction 1, I can fetch instruction 2. Right? So that's how a typical assembly line in a factory works. They'll have a line of cars in different stages of construction. So the first car comes into the assembly line. They may fit the wheels and do something on the chassis. Then it goes to the next stage where they fit the body. While they're doing that, the next car has already entered the assembly line and the wheel is getting fitted. So that's kind of a pipelining. And that's also a instruction level parallelism. It's a very low level, very effective form of parallelism. And it's widely used in x86 processors today. There are multi-stage, 32, 64 stage pipelines in today's processors. So, having said that, we have this comparison to illustrate these things that I have mentioned just now. CPUs have got a lot of cache. They have prefetch logic. They have a lot of good caching logic. They can do branching well. They have high single thread performance, and probably around this kind of so many transistors here. And 10 to 12 cores, 2.8 gigahertz per core. This is a typical processor configuration. Contrasting to that, if you see GPUs, they don't have too much of caching ability. They don't have good branching or single thread performance. What they can do is they can produce high throughput on parallel tasks. They have, like, the Fermi GPU from NVIDIA has 448 cores. Per core, single thread performance may be low, but the sheer number of cores allows us to do large scale parallelism on the GPU and have a high throughput on compute intensive tasks. So a single Fermi GPU for single precision floating point can give me teraflop performance. So basically this is a supercomputer grade. And I have a NVIDIA GPU on my laptop, which probably gives around 250 gigaflops. So that is again a large scale supercomputing ability. So with this, let me show some demos here. So I have this interesting thing called Mandelbrot. This is a pattern generated using fractals. This fractal geometry, and I can scan this pattern I can do animation, change the colors. And right now, all this is running in real time. Millions of computations, floating point computations are happening on the GPU in real time, and it's rendering, and it's very fast. I can do the same computation on CPU. I can, with a one single key press, I can transfer this processing to the CPU. If you see here in this HTOP output, you see all the cores are at 100%. So the CPU is using all its SIMD features, all its multi-core features, whatever parallelism it can give, it is giving. But that is not good enough. As you can see, the animation is jerky, and if I try to move it around, it's very slow. It's not moving smoothly. If I transfer it to the GPU, once again, if you see, the CPU load will quickly go down, and the whole thing becomes smoother. So that's the kind of power that we are talking about here. Similarly, I have this fluid simulation workload, which is this kind of simulates some kind of a watery or oily fluid, and I am doing some things on the surface, so it flows around. All of this is real-time compute. Millions of real-time computations are happening to compute position of each pixel on the screen and plot it. So if I get back to the presentation, there is this thing called as CUDA, which is Compute Unified Device Architecture. It is one of the programming frameworks where you can use a GPU from NVIDIA. There is a equivalent framework from ATI called Stream SDK. That also gives parallel compute capability on a GPU. So can anyone guess what this, how Shah Rukh Khan and CUDA are related? Yes? Have you seen Ravan? How many have seen Ravan? Wow, that's quite less. But anyway, in Ravan, Shah Rukh Khan was wearing this dress, which was having all kinds of lights and special effects and all. Initially, it was a real dress with LED lights and whatnot, and it got damaged after the first scene. And that manufacturing that suit was costing around 2.5 lakhs. So they didn't want to spend so much money every time the suit gets damaged. What they did was, for the rest of the movie, the whole suit on Shah Rukh Khan's body was rendered using CUDA. So that's how they're related. So that's the basic GPU architecture. I won't go through it. I already mentioned there are a lot of processing units, large number of registers, and a lot of memory. The interesting thing is there is this thread execution manager in hardware. So we are not doing thread management in software, we are doing it in hardware. How much?
We're done.
So quickly, if I go through, this is how we do in the GPU. We allocate an array on the GPU. We send the data to the GPU. Then we send the code that we want to execute to the card. It will execute. And then we have to fetch the results back. This is a programming model. And this is this Python example. CUDA can be used from various languages, C, C++, Python, even Java. And these are the industry domains where typically GPU is widely used. We are using it in finance for different kind of risk computation, Monte Carlo simulations. There is scientific computing, weather, and media. So it's kind of a large domain. So that's about it, covering the GPU. There's some performance figures here. Speed up. We have like 18 times, 30 times speed up on some of the financial computations using GPUs.
Okay. Anyway, thanks a lot. I know that we ran a couple of minutes over, but we have if anybody has questions for us about what we went over today, we're going to be over in the main hall. We have a booth right there. We're going to be sticking around for a couple of hours. Any of you want to come by and talk to us about what we spoke about here, we're more than happy to take questions there. I know we're out of time now, so we'll